one thing that you're going to do. And that doesn't make sense, right? We need to see what is the quality of the material coming in, because some things make perfect sense to go into mechanical recycling, but other things just aren't the right quality. And then you also need to think about, what do we want to make on the other side? If you want to keep things safe for food or medical uses, or you need something that's a very high quality, like fluorowire cable, then you need to have these new kinds of recycling technologies. So that's why we're investing in both of the pieces. Okay, that's maybe more than you wanted, but I'll pass it on to Ross.
Sure. Hi, everybody. My name is Ross Eisenberg. I lead America's Plastic Makers, which is essentially the advocacy group representing manufacturers of plastic, taken from the raw material alternative to plastic pellets that then go to everybody to do all that amazing stuff with it. You've probably seen our ads on television or on your phone or both, and if you haven't, I'm guessing the algorithm will catch you pretty soon, most likely because you're in the same room as me. But realistically, our job is to really promote sustainable use of plastic. And so, as an industry, and I should add that we are generally the plastic resin manufacturers. We do have a number of the advanced recyclers in our membership. Frankly, it's been a bit of a niche issue for us over the past few years. We tend to do a fair amount of advocacy in that space as well. As an industry, we have set some pretty ambitious goals for ourselves in the U.S. And they are, by 2030, that all plastic packaging in the U.S. should be recyclable or recoverable, and by 2040, all plastic packaging in the U.S. should be recycled or recoverable. Those are very ambitious goals. I think we all agree with that. It's 2024 already. We've got a long way to go. Getting there, because there, as you know, is no silver bullet, as Jen said. We got to do everything, right? The goal here is to keep the stuff out of the landfill, because from an environmental standpoint, making that chain circular and not linear is environmentally preferable when you look at water, you look at methane, you look at all those things. So keep it out of the landfill. To get it there, you're going to need everything. And a big piece of that puzzle, as we're looking at it, is whatever you want to call it, advanced recycling, right? We call it that in the ad because frankly it pulls extremely well. But realistically, you can't, and more importantly, you cannot do it without it. There is no plan B for the materials that can't go in the mechanical recycler, that can be advanced recycled. And so it's a big piece of the puzzle. We're excited about the progress we're making. There's a long way to go, but thrilled that we're having this discussion today, because I think it's something that there's just so much misinformation out there that if we can actually sit down and have a fact-based discussion, it will help move this ball forward.
Hi everyone, my name is Airhart Holton. Great to be here today, and thanks for sitting in. I'm a principal at MHR Fund Management. We're a private equity structured fund based in New York. We typically invest in middle market companies, look for distressed or undervalued businesses or assets, and really try to figure out how we can add value to those businesses. My background's more of a management consulting, so I spent a number of years focused on oil and gas, which then eventually led into energy transition focused advisory. I had a short spell in the tech world, so started a software business focused on environmental sustainability, particularly for the shipping industry. So software with algorithms that we put on ocean-going vessels, capture operational data, and then figure out how to reduce emissions from operations. So I'm very much not a technical guy, so be warned as I talk through some of the technical issues facing this industry. I'm more of a numbers guy. How do we as MHR and me fit into this discussion? Well, we own a facility in South Carolina called Darling Fibers. Historically, this plant produced polyester staple fiber and chip for the textiles and packaging industries, and it produced this from oil-based raw materials. And so what most people don't realize, and I'll bring a slightly different angle to this discussion, is that polyester, which is a synthetic fiber that's present in 53% of all fibers produced in the world today, PET, it's made with PET, which is a type of plastic. And so I think I've certainly looked into the plastics to plastics recycling world and advanced recycling, but one of the things that we're doing at our site is looking at textile to textile recycling and how do we bring on those technologies to the site to shift away from a world where we're producing virgin polyester to where we can produce 100% recycled polyester. And so the site in South Carolina is a massive site, 765 acres. We recognized several years ago that the technology within this industry, particularly textile to textile, was very nascent. Not a lot of it has been scaled. There's great ambitions and a lot of work to be done, but they still had not scaled to a certain degree. So we've built this campus called Darlington Green, and really the focus is to help incubate a lot of these technologies that can then take glycolysis technology or methanolysis or enzymatic recycling technologies and help them move from lab scale to commercial scale and really help kind of put a dent in some of the recycling issues or lack thereof that we see in the textile space.
Thank you. Bill? I just want to add why we brought this particular group together. Now, there are certainly lots of other people who could speak on this, but each individual here represents a set of ideas and technologies and powers that I think can contribute to the whole. We have other operators that are not represented here who have very large refining facilities who can do chemical recycling all on site and turn it into product at the end of the line. You have Dow, which has more of a partnership approach, which Dow is partnering with a number of other players to be able to master chemical recycling in a way that is maybe more along the line of how an ecosystem operates with different players in the process. Not to denigrate the other approach at all. They all serve an essential role. Aaron, I think what excites us about the technology and the plant, the Darlington Green plant, and Darlington Green is the ecosystem of companies that they're looking to bring together with Darling Plastics, using a variety of technologies, glycolysis, enzymolysis, pyrolysis, and all the other issues that are out there. And the promise there is to extend the technology range of this. And of course, the American Chemistry Council represents all of the companies that are involved in this sector. And Ross and his leadership of the plastic leaders is in a position to bring a lot of these folks together. So, and Recycling Partners are champions and all. So you have here a little ecosystem of power that can drive things in the right direction. Now, they do need to consider things like, there's a concern by some environmentalists, if we get chemical recycling and it is successful, that becomes a dumping ground for all kinds of plastic, and we'll continue to produce all the plastic that we do now, and it'll just be more of a prop for the old fossil fuel sector. And I understand the concerns that people have about that. And I also see the progression of the sector into these nature-based technologies. So I'm sure we'll be getting into those topics as we go.
Yeah, thank you for that. So one of the things we talked about, all the different names for chemical advanced PCM, all those pieces, just so that everyone in the room comes to an understanding, a basic understanding of what we're talking about, what's different than mechanical recycling. Jen here has a great analogy for what chemical recycling is versus mechanical recycling.
I think it might have been Ross's, but I'll take it.
Oh, hey, Ross, are you baking a cake?
I work for Jen, so.
Okay.
Yeah, I'll steal your cake analogy. So you have your milk, your flour, your eggs, your sugar, and you make a cake. And I am going to do the cake pops. So you have the cake, and there's some leftover cake, and you want to make something new. Well, you can mash it up and maybe mix it with a couple of things, and now you have a cake pop. And a cake pop might be pretty delicious, but it's not another birthday cake if what you need is birthday cake. So you need to figure out how can you unbake the cake, which is what we do with advanced recycling. We're going to use that one today. That's what you do, is you kind of feel, how do you pull out those fundamental building blocks so that you can rebuild something that is as fresh and tasty as that very first cake that you had. Did I do it justice?
I had that one wrong. Good job. So one of the things that I do in our time together, we started talking about the different technologies that are out there, right? That's why there's all these different names, there's different pieces on there. And if you don't mind, and Jen, I'll start with you again on this one, is the new technologies out there, the technology frontiers, what breakthroughs are you guys seeing at Dow and what you're working with and your partners, as Bill was saying. And then also, if you don't mind, whenever we talk through these, like what concerns do you see on the other side?
Sure. So some of the technologies that we see, pyrolysis is really common. Sometimes you hear folks talking about gasification as something that might happen in the future. Some of the new evolutions that I see are things like we're partnered with a company called Mura that does a process that they call hydro RPS. So they use water, and I think it's actually supercritical steam, to help break down, to help unbreak that cake into those fundamental building blocks. And because they're using water for the heat transfer, it's a lot more efficient. You get higher yields and a lower carbon footprint, which is kind of great. There's also technologies that are kind of what I call in the middle, right? Where you're not unbaking it all the way, but you can dissolve things with new kinds of solvents that exist. So we just announced a partnership with Procter & Gamble to try to figure out how can we make that work with specifically the polyethylene chemistry. So I think there's a lot of really exciting new innovations, and how can we get down to those more fundamental building blocks. And obviously there's concerns. These are new things that people are worried. Is it going to be safe? Are there contaminants that we need to be concerned about? Do you have the right processes in place? So we're doing a lot of work as an industry to make sure that we understand and better communicate, frankly, the kinds of chemistries that we've been doing for a long time. Frankly, the material that we buy to go into, when you make a plastic, you start with something called an ethylene cracker, if you're in the US, and you break that ethylene down into something that we can build up into something that we call a polyethylene. We have very stringent specifications for what goes into those giant plants. And then it goes through, one of my German friends called it the hellfire of the cracker. Because again, you are doing this incredible chemistry to get it down to the little tiny pieces to rebuild it again. So we have a really good handle on what the chemistry is to make sure that the products are safe. We have a long history of monitoring air to make sure that the air is safe, monitoring the water to make sure that the water stays safe. I appreciate all the work that your industry does, helping us with Operation Clean Sweep to make sure that even our pellets are being managed appropriately. But we need to be involved with our communities and making sure that we're meeting their needs and being good partners and helping them.
Aaron, I want to go over to you real quick. Your view of this not from a technology supplier or a supplier in the market, you're incubating technologies in there, and you're in the textile space. When we get to sit down and talk, I hope everyone in the room kind of got that right. It's not just bottles and cans and packaging and things that we're talking about out here. It's textiles, right? So what are you seeing from the technologies that are coming to you and that you're looking at to put in there? And then what concerns do they have about their viability, or what concerns are you seeing from them on the textile space?
Yeah, absolutely. I mean, I think one of the things with textiles is relative to plastics, it's still at such an early stage. So I saw a stat yesterday that less than 1% of textiles are recycled into a new textile product. So very shocking and low numbers. And so when we see a lot of the technologies exist, many of them are even some of the same ones that Jen mentioned. So there's glycolysis technologies, methanolysis, there's enzymatic recycling. In terms of some of the advancements that are out there, we even see some technologies that are using AI to better select enzymes that can be processed in a much more efficient manner. So there's certainly a lot of interesting technologies that are out there. I think some of the challenges that we're seeing all come down to technological barriers around collection and sortation. So you think of your golf shirt. It's not a simple, hey, this is a polyester shirt. It's similar to a plastic bottle. There's going to be probably multiple blends, or it will be mixed plastics, the same thing with a shirt. So you have maybe a 50-50 polyester cotton blend, you have buttons, you may have zippers, you may have all kinds of things on there. And so a lot of the challenges that these technology companies face are how do we deal with the sortation of these materials? It's very manual in nature. And so we struggle to scale from that perspective. And then again, there aren't many shirts that are going to be plain white or plain black shirt. You have mixed materials, you have mixed colors, and so how do you deal with all these things in an efficient manner that can then be scaled? It's challenging, not to mention the technical challenges and barriers that we all know is, I think, the big knock on advanced recycling is that many believe that it's much more energy intensive or can be much more water intensive depending on the technology in use. So there's constant evolution and desire to try to figure out how do you reduce energy intensity, how do you reduce water used in the process, or maybe how do you recycle that in? So if you're using water, how do you capture that at the end of the process, purify it, and then put it back into the process so you have a circular loop where yes, you need water, but you're not having to continuously pull on freshwater solutions, or if you're using monoethylene glycol in a glycolysis reaction, that you're able to recycle that back and thereby reduce your usage of chemicals in the process.
Some of the skepticism of advanced